Hello everybody, my name is Akhan and today my topic in presentation is measuring exoplanets with the transit method. Okay, so first of all, what are exoplanets? Exoplanets are the planets that orbit a star other than our sun. That means all the planets that are outside of our solar system are known as the exoplanets. Methods for detecting exoplanets. Okay, exoplanets detection methods. There are many detection methods for exoplanets, but these are the top three or the most famous and effective three detection methods. That is the radial velocity method, direct imaging method, and transit method. First of all, we'll see the radial velocity method. As we know, the gravity pulls on everything. Star pulls planets, and the planet pulls stars, as we can see in this animation. We can sometimes see this pull when a planet is tugging on a star either towards us or away from us, making a star appear bluer or redder. This is due to the Doppler effect, which shifts the wavelength of the star light. For the same reason, an animal cell changes pitch as it passes you. And also in this animation, we can see that star is applying gravitational force to the planet, and the same process the planet also applying gravitational force to the star. By applying both gravitational forces to each other, we can see that in wobbly motion means the center of gravity is moving. Okay, on the right, you can see the plot of this radial velocity. So the next is the direct imaging method. In direct imaging method, means the astronomer hide the glare of the star or the brightness of the star, and the only visible part is the we can see the planet. This the yellow dot. This is the planet, and this is the images from December 2014 to September 2018. We can see it makes a complete orbit. This point is the Peter Pictoris B is one of the few exoplanets that scientists have been able to photograph so far. A series of images from Eastern Green Large Telescope shows it orbiting its star. And by taking all the images, the animation will look something like this. The yellow again, the yellow dot is this yellow spot is the exoplanet. Okay, the most important and effective method is the transit method. Most known exoplanets have been discovered using a transit method. The transit occurs when a planet passes between a star and its observer. Because a planet passing in front of its star ever so slightly dims its light. Okay, so exoplanet light curve dips. Okay, there is I like to show an animation in which you will see the importance of the dips and what are the dips. Means when the starlight is blocked by the planet, what happens to its flux? Okay, so first of all, we can see that on the left we have the blue, that is the larger planet, then the white one, which is the red, the smaller planet. Below it is light versus time graph. Now, as we know that when the planet blocks the starlight, the dip is produced. And this dips, by looking at these dips carefully, we can see that the larger the planet makes the greater the dip. The smaller planet makes the smaller dip. Also, this is important for the orbiting period is how far or near the star is, how far or near the planet is from the star. Okay, moving Moving further, we have multiple divergence transfer. Okay, so there is another interesting phenomenon in which the star system, many planets blocking the starlight, and how the plot will show. So, okay, so we can see that this is a system of a. We can say that it's another solar system beyond our. We can see that the first star passing by creating a dip or a light curve. The second, but the smaller one, is blocking the starlight and it enters and can. But now something interesting will happen. You can see that the first one, the larger one, the dip was the larger. The second was the smaller than the first one. The dip was smaller than the first one. But before leaving the star, another planet enters and blocks the light. You can see how the dip suddenly changes. This is a very interesting part, interesting kind of stuff. But yes, we can again analyze from these dips also. This is not, but yes, we have to do some extra work to filter the dips, but it will work. Okay, so analyzing Kepler 6b and 4b using Jupyter notebooks. After getting the data of Kepler 6b and 4b, I analyzed these two planets using Jupyter notebooks and plotted some of the slide curves. We can see in this image, and we all have seen these images previously, but I would like to show Kepler 4b and Kepler 6b. The dips, concentrate on these dips. The dip Kepler 4b dips is lesser, and Kepler 6b dips is much larger. So just by looking at the dips, we can see that Kepler 4b is smaller than Kepler 6b, and Kepler 6b is the larger among these two. And another interesting part, you can see that the orbital period for both the planets Kepler, that is the Kepler 4b and Kepler 6b, are same, which is 3.2 days. And verifying our results, we can see that at the last Kepler 4b, size of the Kepler 4b is 4.31 times the radius of Earth, and Kepler 6b is 15 times the radius of Earth, which again proves that the curve shows the how the curve and the size are linked together. Okay, so this was the result which we already know, but now it's part of analyzing both the data. Okay, so now I plotted the light curves plot without using mod function or the model function. The above one is the plot for the Kepler 4b, and the below is the plot for Kepler 6b. Kepler 6b plot is kind of a neat one as compared to the 4b, because the planet was planet blocked Kepler 4b blocked the light for the less period of time because it was small, so the light blocked by it was a bit less. Okay, moving further, again the light curves were plotted, but this time by using the mod function, using model function. So now we can see that we have a tiny graphs, means the tiny graphs in which we can see the Kepler 4b has a tiny dip on the left side, and Kepler 6b, the below one, is dip a larger dip. After further processing means setting the colors of the plots, the dots, and applying the legends, and so the final image of my plot looked something like this. The left one is the Kepler 6b, and the right one folded curve of Kepler 4b. And my calculated results of Kepler 4b and 6b were orbital radius of Kepler 6b 0.04 astronomical unit, and orbital radius of Kepler 6b was almost the same. So by the previous image, we know that the orbital period was almost same for both the pairs, which was 3.2 days. And over here, we can see that the orbital radius is almost same also. So the radius of Kepler 6b is 1.4 times the radius of Jupiter, and radius of Kepler 4b is 0.36 times the radius of Jupiter. Again, it shows that the Kepler 4b radius is lesser than the Kepler 6b, which again tells us that Kepler 4b is the smaller planet. And temperature of the Kepler 6b is 2088 Kelvin. Temperature of Kepler 4b is 2240 Kelvin. So Kepler 4b is temperature-wise greater than Kepler 6b, and it is smaller than Kepler 6b. Mass of the Kepler 6b is 0.61 times the mass of Jupiter, and mass of Kepler 4b is 0.09 mass of Jupiter. So the mass of the Kepler 4b is way more lesser than Kepler 6b. The density of the Kepler 6b is 0.3 grams per centimeter cube. The density of Kepler 4b is 0.04 grams per centimeter cube. To compare the densities, a real value of density of water. By comparing the both densities with the density of water, which is 1 gram per centimeter cube, we can see that if how the density, how less the density is of Kepler 4b and even the Kepler 6b. And if we and you can see that if we put Kepler 4b or Kepler 6b in an ocean, it will flow. And the last part of this analysis was the composition. Kepler 4b and Kepler 6b, we knew the radius of the Kepler 6b and 4b, and also the mass of the Kepler 6b and 4b in terms of the radius of the Jupiter and mass of Jupiter. Kepler 6b was radius of Jupiter was 1.4, and mass of the Jupiter for Kepler 4 in terms of mass of Jupiter was around 0.09 to 0.078. And in Kepler 4b, the mass, the radius of in terms of radius Jupiter was 0.4, and the mass in terms of mass of Jupiter was 0.07 or 0.08. So the plot shows that for the Kepler 4b, the planet Kepler 4b is almost have the composition similar to Neptune. And you can see from the plot that the Kepler 4b has pure rock between the pure rock and the pure ice, and it kind of have around 7 to 10% of hydrogen and helium. And for the Kepler 6b, you can see that it's pure is above the pure hydrogen and helium. Its composition is purely hydrogen and helium. So let's continue the presentation. Thank you everyone.